Hi, this is Tim Hodges, and here's a quick video about how to differentiate and integrate power series and how to use this technique to find new power series representations of some familiar functions. Let's start with the basic theorem about differentiating and integrating a general power series. So let's consider a power series centered at A with radius of convergence R. Then this defines for us a function whose value is the sum of the series where it converges. The main theorem says that this function is differentiable and therefore continuous on the open interval from a minus r to a plus r. So this is essentially the interval of convergence of the original function, not worrying about the endpoints. The derivative and integral are exactly what we would expect if we were differentiating or integrating a finite polynomial. So essentially, we just integrate and differentiate each term individually and take the sum of that new series. So the derivative of f of x is n times the sum of n times cn x minus a to the n minus 1, and the integral is the sum of cn x minus a to the n plus 1 divided by n plus 1 plus, as always, an arbitrary constant. Importantly, the radius of convergence of these two functions, the derivative and the integral, is the same as the radius of convergence of the original function. It's again r. Let's have a look at the simpler situation where the power series is centered around 0, i.e. when a equals 0. This is a Maclaurin series. So if we have a power series sum cn x to the n with radius of convergence r, then again we have the function f of x given by the sum from 0 to infinity cn x to the n. And this is differentiable and continuous on the interval now from minus r to r, since we're now centering at the origin. And the derivative is just the usual derivative you see here you'd get if you thought of this as just an infinite polynomial. So derivative of c0 is 0, derivative of c1x is x, derivative of c2x squared is 2c2x, etc. And so if we look at the summation form of this, the original function was the sum n equals 0 to infinity cn x to the n. And we just differentiate each of these terms individually and take the new series we get by adding these all up. So the derivative of cn x to the n, of course, is n times cn x to the n minus 1. And we just sum this series from 0 to infinity. Of course, that's the same as summing it from 1 to infinity, since the n equals 0 term is always 0. The integral similarly is given by integrating term by term. So c0 integrates to c0x, c1x integrates to c1x squared over 2, etc. And the general form of this is cn times x to the n plus 1 divided by n plus 1. We sum all that, and then we add an arbitrary constant. And again, as before, the radius of convergence of these two new functions is still r, the same as the radius of convergence of the original series. Okay, let's have a look at how we can apply this and also see how we can find new power series representations of some familiar functions. Okay, let's start off by differentiating. Let's start from our classic power series representation from a geometric series. So we know that 1 over 1 minus x can be represented as the sum of x to the n from 0 to infinity. So 1 plus x squared plus x cubed, because it's a geometric series with initial term 1 and ratio x. So this will converge. This equality will be true when x has absolute value less than 1. Differentiating the left-hand side gives us 1 over 1 minus x squared. Notice that we're using the chain rule here, and there's a couple of negative signs that cancel out there. Differentiating these closed summation, we get the sum of n times x to the n minus 1 from 0 to infinity. And differentiating it term by term, we get 0 plus 1 plus 2x plus 3x squared, etc. And this equality will still be true precisely when x has absolute value less than 1. Now, this is not in the usual form that we want. We usually want to represent a power series as something, a sum of x to the n. So let's shift the index. So we do this, we want to replace n minus 1 by n. So let's first give it a different name. Let's let k be n minus 1, and let's represent this sum in terms of k. First thing we note is that the n equals 0 term is 0, so that's the same as the sum from 1 to infinity of n times x to the n minus 1. We now replace n's by k's, so the n minus 1 in the power becomes k, the n becomes k plus 1, and as n goes from 1 to infinity, k goes from 0 to infinity, because when n is 1, k is 0. So this gives us a more normal form for this summation, and now we can replace the k's by n's to get the classic description of the fact that 1 over 1 minus x squared is the sum n equals 0 to infinity, n plus 1 x to the n. And if you look back up here, you see that's exactly what we've got. We've got the sum of the powers of x multiplied by the power plus 1. 1 plus 2x plus 3x squared plus 4x cubed, etc. So differentiating 1 over 1 minus x gives us the power series representation of 1 over 1 minus x squared. And obviously we can keep repeating this to get the power series representation of 1 over 1 minus x to any power. Let's have a look at integration. Let's start off with another classic power series representation that we know, 1 over 1 plus x squared. This is the sum of a geometric series with initial term 1 and ratio minus x squared. So it's equal to the sum minus 1 to the n x to the 2n from 0 to infinity, which looks like that. And this summation, this equality is true when x has absolute value less than 1 again. We integrate the left-hand side, remember we get arctan of x, and integrating the right-hand side, we just raise the power of x by 1 and divide by the new power. So we get the sum n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1, which we look at it term by term, looks like x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc. And this equality will again be true when x has absolute value less than 1. Interestingly, with a little bit more work, we can show that the equality actually holds also when x is equal to 1. Notice that the alternating series test tells us that the series does converge when x is equal to 1. And so that gives us the very interesting equality that pi over 4, which is arctan of 1, is 1 minus a third plus a fifth minus a seventh, etc. So it's the alternating sum of the reciprocals of the odd numbers. Curious. Okay, so let's summarize what we learned in this video. We learned that a function given as a power series can be differentiated and integrated in the natural way, just as if it was an infinite polynomial. We learned that the integral and the derivative have the same radius of convergence as the original function f. And we saw a couple of examples of how we can use this to find power series representations of new functions.